The most notable characteristic we see in trees in real life are its branches sprouting from a main trunk. In computer science, as what it is named from, a tree data structure is a way of storing data with the use of different branches, or in our case, different nodes. In this video, the first thing that I'll be talking about is defining trees. What are trees? Next, I'll be discussing some variations, just in a general manner so that we would have an overview of how trees can be used in programming. Then, in most parts of this video, I'll be focusing more on about the binary tree data structure and how we could traverse through it. And then, I'll be talking its applications so that we would have an idea or reason why we're learning this data structure. Now let's define what a tree data structure is. Assuming that you already have some background knowledge of data structures and other data structures, a tree is very much similar to the previously mentioned linked list data structure. As we know, linked lists store data with pointers from each storage containers. Or for the sake of this video, since we'll be using this term more often, let's refer to these storage containers as nodes. Now, again, linked lists have pointers for each node that points to other nodes. Although, for a tree data structure, each node has different pointers that would point to different multiple nodes. Another point that I would like to mention is that in real life, trees commonly go upright, while in computer science, we usually talk about trees in an upside down way. In a more formal computer sciencey context, we have terms to easily refer to these nodes to better organize our thoughts when working with a tree data structure. The first term is the root, which basically just refers to the first node that is connected to all the other nodes in the tree data structure. In other data structures, this term could be called
There's
as the
also
head.
the term parent, which just refers to nodes that have nodes connected under them.
Additionally, the root is the only node in the structure that doesn't have a parent node, and there are those nodes that are called under the parent nodes, which we call children nodes. And then we have nodes that doesn't have any more nodes connected below them, which we refer to as a leaf node. There are actually more terms that is used by other people, but for this video's sake, I'll only be mentioning these four terms. If we put it into words, we define tree as a collection of nodes that is stored in a tree-like manner. Compared to other data structures, data is not linear, which means it doesn't go in a line but goes with multiple branches. In the real world, the tree data structure is used in file system storage, and it is used in mathematics, calculation, and decision making, and it is commonly more used on sorting. Now that's just it for some general definition of what tree data structures are. But defining it alone with words does not necessarily mean we already understand the concept deeply in a computer science level. So let's talk more aspects about it and see how it really works. One thing that would really help our understanding of it would be to know how to traverse through it on how to access the elements. But first, let me tell some variations of a tree data structure and talk more about one of the most used variation called the binary search tree. Now, for the variations of the tree data structure, there will be a lot that I could talk about regarding these variations, and I could go in depth for each one of them, but I will only somewhat be discussing some of them generally, except for the binary search tree, which I will discuss more of in the later parts of the videos. And then since most of these variations are just under the binary tree variation. As I said, one of variation of a tree is the binary tree, and we have more variations of it, or should we say extensions, which are the binary search tree and the threaded binary tree. There are also those variations which we can classify as something that is also under the binary tree classification and also under the self-balancing tree classification. Some of these self-balancing trees are the red-black tree and the AVL tree and the B tree. Now, for the binary tree, for this part, I will just give some general introductory definition of a binary tree, but I will go in depth on it later on. But for now, a binary tree is basically just a tree with at most two children nodes for each parent nodes. From the word bi, meaning two, the binary tree is what is mostly used in computer science and programming, and it has a lot of variations that which can be classified under this general binary tree. And then for the self-balancing tree, we have these variations, which are the red-black tree, AVL tree, and B tree. There are actually a lot more than three, but for this video's sake, I'll only be talking about these three. These three variations, in essence, just have the same functionality, but each of them has their own different advantages and disadvantages. Now, for the definition of a self-balancing tree, for before that, we need to remember that there's always this process where we try to insert an element to our data structure. And what happens in a tree data structure is that when we don't have a self-balancing tree, the data just goes like this, which is, in definition, is just a linked list. But for self-balancing trees, what happens is that when an element is inserted, the algorithm is designed for it to balance itself. Instead of it going like a linked list, when an element is inserted, the tree balances itself and places the inserted element together to the free space on the height before it. And when further elements are to be inserted, it just continues this process to keep itself balanced. Hence the word self-balancing. As previously mentioned, there are variations of a self-balancing tree, just like the red-black tree, where each node has a color red or black. It can be visualized as this, where the colors of the nodes are just used to make sure that the trees remain approximately balanced during insertions and deletions. Another variation of a self-balancing tree is the AVL tree. The acronyms AVL came from its Russian inventors Adelskin, Velsky, and Landes. The way how it works can be visualized as this animation, which I got from its Wikipedia page. Basically, what's important to note is that it allows the tree to also have a further balanced height by undergoing rotations. In a more formal written code, this rotation is aided by the balance factors, which are the numbers -1, 0, and 1. Another variation is the B tree, which in general definition is just a tree that contains multiple nodes which keep data in sorted order, where each node has two or more children nodes and consisting multiple keys. Additionally, and to point out, these variations are made since it enables our program to run much faster, since all these variations that I talked about aids the programmer to write algorithms that run at a time complexity of O of log n, which in other words just means that it is faster or much efficient than most data structures in specific scenarios. And that's just it for the variations. It's important to note that I somewhat just presented those variations in a general manner. There can be a lot of things that could be discussed in those variations, and we could go in depth for each one of them. I just want us to have an idea that there are many ways we can implement or create the tree data structure. Now, to further understand the tree data structure, I will be talking about how we could search or traverse the elements in the tree. This is usually referred to as the binary search tree because we will be trying to look for the elements in each node. In formal code, this is how we implement a binary search tree. This is a Python code which I got from some website. I purposely made it too small and unreadable because the formal code is kinda too technical to understand. Instead, what I will be doing is to explain it in our own humanish programming language. So just like any data structure, the first thing that we need to instruct the computer is what it should do when we insert an element. When we want to store elements in a binary tree, and let's say, for example, numbers, what usually happens is that we would write our code in which, when we store the elements, the greater element goes to the right side, then we store the lesser one in the left side. This way of storing or inserting an element is helpful later on when we traverse the elements in the tree. First, we say to the computer, hey, place the first element as the root node. And then when more elements are inserted, we say to the computer when the element is greater, it should place it on the right side, or it should be the right child. Then, if the element is lesser, we place it to the left and it becomes the left child. Now let's visualize this. Say we were given the data 30, 13, 45, 10, 5, 11, and 92. When we insert our first node as what we instructed the computer sets the first element inserted as the root node. Next, when we insert the next element, in this case 13, the computer compares 13 to 30. Since 13 is lesser than 30, 13 goes to the left node. Then, when we insert the next element, 45, since 45 is greater than 30, 45 goes to the right node. Then, for the next element, 10, since 10 is lesser than 30, it goes to the left node. And since there's already another left node, it 10 then compares itself to 13. And since 10 is still lesser than 13, it goes to the left node of 13. Then, when we insert number 5, since 5 is lesser than 30 and it is also still lesser than 13 and it is still lesser than 10, it goes to the left node of 10. The next element is 11. Since 11 is lesser than 30, it still goes to the left. And since 11 is lesser than 13, it goes under it, and the computer then compares 11 to 10. Now, since 11 is greater than 10, it now goes to the right side of 10. And now, for the next element, 92, since 92 is greater than 30, it goes under it to the right. Then the computer then further compares it to 45. Since 92 is greater than 45, it goes to the right side of 45. Now we have all the elements inserted in the tree. Now let's visualize it again using the website from the University of San Francisco for a cleaner way of visualizing this. As you can see, we did the same thing where we placed the lesser element as the left child, and then we placed the greater element as the right child, each while comparing it first to the root node, then to the next nodes. Now that's just it for inserting the elements. It may not look like it, but the elements here are actually already sorted. That means that the numbers here are actually already in order. But how is it exactly sorted? This is where the traversal or searching comes in. But for now, let's try and make instructions for traversing the elements. Earlier, we made an instruction for inserting the elements. Now, let's create instructions for how to traverse the elements, or should we say, print the elements. But before we start writing instructions about how to traverse a tree, I'm going to mention that there are actually three methods we can traverse the elements inside a tree data structure. These three are known as the pre-order traversal, the in-order traversal, and the post-order traversal. And what we commonly use as a traversal, especially in a binary search tree, is the in-order traversal. And so what we're going to use in this video is the in-order traversal. So now let's start writing the instructions. What we're going to say is that we're going to tell the computer that, hey, for each node, if you have a left child, visit it. And then, if you no longer have a left child, print the current child or the node. And then we say, check it further if you have a right child, visit it. If not, just go back. And then we're gonna say that keep doing this until you're done. So now, let's visualize the instructions that we've written. So when we ask the computer to print out all the elements inside a binary search tree, the computer first asks the first node, do you have a left child? Since it has a left child, it will visit it. Then, when it is already at that child, it will ask again if it has a left child. Since it has a left child, it will visit further since it has a left child under it. Then furthermore, since there is still a left child, it will visit that child. Now, it reaches a leaf node, meaning the node no longer has a left child. Based on the instructions we've written, the computer asks if there is a left child. And since there is no left child, the computer then prints that current node since that was the instruction written for it. Then, we have here our output. The number 5 is printed. Then, if we go back to the code we've written, it says that after it prints, the computer then checks if it has a right node or a right child. Since it does not have a right child, it will go back to its upper parent node. Also, it is important to note that after it is printed, the computer then disregards that node. Now, we are on the node of number 10. The computer asks again if it has a left child. But since it no longer has a left child, it will print that node since it is where we're currently visiting. So the number 10 is now printed. After printing, again, if we look back to our instructions, the computer then asks if it has a right child. Since it has a right child, we then visit that right child under it. Basing again from our instructions, we first ask if there is a left child. Since there is no left child, it will print the current node, which has number 11 in it. And then, basing our actions from the instructions we've written, we ask if there's a right child. Since there is none, we go back to the upper nodes. And since 10 is done, we go back further up to the node of number 13. And based on the instructions we've written, we can print out 13 since it no longer has a left or right child. And then, repeating the instructions that we've did, we go back to the upper node, and now we are in our root node. Then the computer then performs the instructions we've written. It asks if there is a left child, and since there is no left child, it just prints the current node, which is the root node. Now we are done with the node. We then ask if there is a right child, and since there is a right child, we go to that node. Basing again from our instructions, since the node for 45 does not have a left child, we then print out the node of 45. And then, based on the instructions we've written, the computer then asks if it has a right child. Since it has a right child, for a cleaner visualization, let's use the website earlier from the UCFA to have a cleaner visualization of how we printed out our nodes. As you can see, the binary search tree prints out the elements in order, from descending to ascending. And that's just it for the binary search tree. The point of discussing this is for us to have an understanding of how to traverse a binary search tree, and also for us to have our foundational understanding of all the tree data structure. And by this, we would become flexible programmers since most of the other variations are just similar to this, the binary search tree. Now, for the last part, let us see the applications of the tree data structure. I've mentioned some of these before in the earlier part of this video, but now since we have some deeper understanding, it's helpful if we go back to this so we would be able to clearly drill in our heads its practical application in real life. One of this is about file system management. As you can see, when I type in tree in the command prompt, we could actually see a visualization of our files in a tree data structure. Another application of this would be about mathematical operations where, for instance, when we create really complicated calculators, it can help us organize the operations involved in the mathematical expression. Another application are routing algorithms, which are used for the purpose of deciding which route an incoming data needs to be transmitted to reach a destination efficiently. Another one is searching and sorting, since as mentioned, the tree data structure is efficient since most operations run on a constant time of O of log n, which is fast compared to other data structures.